In this video, we're going to look at the effect of the benzene ring on reactive intermediates that we've already had, most specifically carbocations and free radicals, and we're also going to look at its effect on the SN2 reaction as well. All right, so a carbocation directly adjacent to a benzene ring, like this one right here, is going to be referred to as a benzylic carbocation. All right, this is more stable. This looks like a primary carbocation, but it's actually much more stable than your typical primary carbocation because of resonance. We can delocalize the carbocation, or the positive charge, into the benzene ring, like so. All right, so we can write a resonance structure like that, which now gives us this resonance structure here. All right, we can continue doing that all the way around the ring. Okay, so we can write a resonance structure from that set of arrows, and this gives us this, and we can go one additional further to delocalize it again. So we see here is that with the benzylic carbocation, we are delocalizing the positive charge into the ortho and para positions. Okay. All right, so ortho, para, the other ortho. All right, now of these three carbocations, what's the most stable one? Or what's the best what's the one that's going to really explain our reactivity? It's this one right here, the first one we started with. And the reason, of course, is because that's the only one of the resonance forms that retains the benzene ring. All right, we can write a similar set of resonance structures with the free radical. Okay, so here we can delocalize the spin over to the ortho position. Okay, so we'll do half arrows here. Okay, and what we see now is that our radical is now delocalized to the ortho position. We can continue doing similar resonance structures. We get it at the para position here and at the other ortho position here. Okay, so we delocalize the spin into the ortho and para position, or the unpaired electron is delocalized into the ortho and para positions. Okay, when we're looking at allylic free radicals, we had to consider all the resonance forms and the products arising from all of the resonance forms. But we don't have to with the benzylic free radical, because this over here is overwhelmingly the most important one. This is, again, the only one that retains the benzene ring, and all of the products are going to arise from that resonance form right there. All right, the SN2 reaction. We also see a situation where the benzylic systems are faster. All right. And this is because when a bond is at the benzylic position, it's weaker, just like it is at the allylic position. So we have a head start right there. The bond to chlorine is weaker than the typical bond of a primary carbon to chlorine. Okay, so that's going to help us out a little. And we also have a situation where the transition state for the SN2 reaction, remember this 5-coordinate intermediate where as the nucleophile is coming in, the bromine is coming out, but this intermediate has a p orbital here, and this p orbital can enter into a conjugation interaction with the benzene ring, and this is going to be activating to the SN2 reaction as well. So we see that benzylic systems occur faster than the analogous primary systems over here. All right. Also, I'm going to add another issue here that also helps out the SN2 reaction. There's no hydrogen here. Okay. Thus, the E2 can't compete. Okay, so when we have this primary system here. All we have to worry about is the SN2 reaction. All right. Okay, so let's look at what we just learned and see how we can answer this question here. Which compound undergoes solvolysis reactions at the fastest rate? And our solvolysis reaction here is we're just going to heat it in methanol, use methanol itself as the nucleophile, and get the methyl ether. Okay, we're going to get as a byproduct in both of these cases HCl2. Okay, so let's not forget that. All right, so what do we know about solvolysis? Okay, well, if you remember from chapter 8, they're all SN1 reactions, and they proceed through carbocation intermediates. Okay, so methanol is such a poor nucleophile or a poor base that it cannot react with the halide directly. It can only react with the carbocation that you get by dissociating the halide. Okay, and that's why we have the first order reaction. All right, so solvolysis is an SN1 reaction. All we have to do to determine which reaction is faster is just compare the relative stability of the carbocations. All right, this carbocation right here is tertiary and benzylic. It's thus better. All right, the carbocation right here, it's just tertiary. That's not as good as being tertiary and benzylic. Here, in the benzylic case, we have resonance stabilization in addition to the hyperconjugative stabilization of a tertiary system. Here we have no resonance stabilization. We have some seriously good hyperconjugative interactions. Okay, a lot of them, but we don't have resonance, and resonance is a more important stabilizing influence than is hyperconjugation. Okay, so reaction A is going to occur at the fastest rate because it proceeds through the more stable, resonance stabilized carbocation. All right, let's look at another one. This is actually identical to an exam problem a few weeks ago. And in that one, I told you that the benzene ring stabilizes a carbocation better than a methyl group, and asked you to just figure out which one you would get. I told you not to worry about why. Now we're going to look at why. All right, so hypothetically, HCl can add to this alkene to produce either of these two products, the benzylic chloride or the chloride that's just secondary. All right, so if you remember the mechanism for this reaction, it involves protonation to form the carbocation. Okay, so let's just draw the arrows for that. Okay, I might have already drawn them, but I'll just draw them for fun here. All right, so there's our first step. Okay, looks like I did draw them just for fun. All right. All right, so this initial formation of the carbocation can produce either this carbocation right here or this carbocation right here. The carbocation at the top is secondary and benzylic. The carbocation here, it's just secondary. So this one, again, has resonance stabilization. Okay, so whereas the other one does not. And remember that this reaction is governed by the stability of the carbocation intermediate, right? So we're expecting all of the product to arise from the more stable carbocation, this one right here. All right, so we expect the product on the left to be the product, okay? So this should be our major product. Or I guess I wrote it down here that it's the expected product. Okay, all right, let's look at this one down here. What's the product of this reaction here? This iodide here reacting with KOH ethanol. Are we going to produce the SN2 product, or E2 product B, or E2 product C? Okay, the things to note here are that this halide is secondary. This is a strong base. It's an oxygen, which is in the top of the periodic table and thus not all that high on the nucleophilicity scale. And we're going to say that we're probably going to engage in an E2 reaction. All right, so we should be seeing either B or C, because B and C are E2. This is SN2. All right. Now, which would be the major product? Well, compound B, we can look and see right here, we have a conjugated system embedded within the molecule. Okay, whereas C is an isolated alkene. Okay, there are sp3 carbons separating that alkene from the other pi system. So we're going to expect B to form because B is conjugated. And remember that the E2 reaction, if there's not any like stereoelectronic things going on, it goes by Saitsev's rule. We preferentially produce the more stable alkene. All right, let's predict the products of this reaction, and we're going to provide a mechanistic rationale as to why your product and no other product forms. All right, so here we're going to treat this with NBS and light. All right, we could, all of the hydrogens we could potentially replace are hydrogens at secondary carbon. This carbon down at the bottom is just like those. All right, but we're going to see that we're going to get exclusive bromination at the benzylic position, okay? And this is because this product forms via the benzylic radical. This radical is secondary and benzylic, okay? So we can write all these resonance forms where the free radical site is delocalized into the benzene ring. Okay, but we're going to see only attack at the benzylic position because all those other resonance forms destroy the aromaticity. Okay, but they do serve to stabilize the reactive intermediate to some extent. All right, this alternative free radical that we got by removing one of these hydrogens here is just secondary, and that is not as good. There's no direct stabilization of this free radical right here by resonance. All right, what about this one? This next one, we have a set of hydrogens here that we could call secondary and doubly benzylic, because they're benzylic relative to both rings, whereas hydrogens here are secondary and singly benzylic. They're only have a benzylic relationship to one ring here. All right, we're going to see that this compound right here is in fact going to be our major product. Okay, and when we look at this radical here and all of its resonance structures, we can see that we're going to delocalize it to the ortho, para, ortho position of the other ring system here, and we can see in the other that we're also going to do exactly the same thing in the other benzene ring, ortho, para, ortho. So this radical is stabilized by a lot. The alternative free radical, the one that you get by just removing the secondary and singly benzylic hydrogen, is here. This is pretty good, but it's not as good as this one right here, which is benzylic to two different benzene rings. Okay. And the last one, we also have a selectivity issue. We have secondary benzylic hydrogens. Hydrogens at secondary carbon hydrogen at tertiary carbon. We have hydrogen at primary carbon. We're going to see exclusive formation of the compound, which is the benzylic chloride. This is because only the benzylic radicals have resonance stabilization, and that's better than the stabilization afforded to the primary, secondary, or tertiary radicals that you get from extracting any of the other hydrogens. Okay, all right, let's just write a detailed mechanism for the first one, since we haven't written a mechanism in a benzylic system. All right, so this is the reaction we're going to look at. We have our starting material, NBS, going to the benzylic bromide, and the byproduct from N-bromosuccinimide is just the succinimide. Okay. All right, so let's recall from previous discussions that we have this equilibrium here, where NBS is reacting with our HBr byproduct to make the succinimide and generating bromine in a small, continual, low concentration situation. All right, so in our initiation, we're going to treat this with light to just cleave the nitrogen-bromine bond, and this gives us the nitrogen radical and bromine radical. And we could also imagine that there be some bromine here, so we're going to say bromine could react with our light to make two bromine radicals. Either way, the net result is that we're making these radicals to start our propagation process. All right, so in our propagation, I'll just draw the half-headed arrows here. Okay, we're making the benzylic radical and HBr. HBr then starts to engage in this reaction up here to produce some bromine. All right, this is now going to react with bromine and an bromine atom abstraction reaction to generate our other product, and our bromine radical is going to re-enter the cycle up here, and this is how virtually all of our product forms. There's some termination steps where you take any of these free radicals and randomly combine them, but the most important part of the product formation occurs in the propagation. All right, we're going to do one more problem, and then we're going to look at take a deeper look at aromaticity in the next video. All right, so let's predict the product of each reaction. All right, so when we look at the top reaction, we see primary benzylic, primary, and we see a good nucleophile. Okay, really the only thing that we could reasonably expect from this reaction is an SN2 reaction. Remember, benzylic positions are activated relative to simple primary positions, and the expected product with 1 mole of sodium azide would be the benzylic azide that you see right there. Okay? All right, so that's our expected product of this one. We should see preferential reaction at the benzylic position if we're comparing benzylic in primary versus just primary. All right, here we're treating this with sodium, or like the allyl sulfide anion that you see here. And here I'm going to say we're going to add as many moles as we want. And this is another example of the SN2 reaction. This is primary and benzylic. This is bromine at sp2 carbon, and remember that this type of halide is inert in the SN2 reaction, so we can only reasonably expect this reaction to occur right there. Okay, remember that we have to regard this as being an ionic compound. So of the two species Na plus versus its counter ion. That's the most important part of this. And this produces the product that you see here. Sorry. Okay. In this last one, we're going to treat it with sodium methoxide and DMSO. All right. So what we have here is a situation where we have SN2 versus E2. We're not going to consider any of the first order reactions with this base. This base is too strong. Okay. So we would not see an E1 or an SN1 with this base. Okay. All right. So this is tertiary and benzylic. Somewhat lousy for the SN2. So we're going to see the E2 predominate, and this is the expected product of this reaction. All right, so in the next video, we're going to take a deeper look at aromaticity and how it applies to other conjugated systems beside benzene and higher fused benzene analogs.